Before we begin, I kindly request you to subscribe to the channel and click the bell icon to stay updated with our latest videos. If you enjoy the content, please don't forget to like and share it with your friends and colleagues. Now, let's get started. In this reaction, we are looking at an example of the Pinacol rearrangement, where a vicinal diol is converted into a ketone through carbocation rearrangement under acidic conditions. First, observe the starting molecule. It contains two neighboring hydroxyl groups, which is the typical requirement for the Pinacol rearrangement. Step 1. Protonation. Under acidic conditions, one of the hydroxyl groups becomes protonated. When the OH group gains a proton, it becomes OH2+, which is a very good leaving group. Step 2. Loss of water. Next, the protonated hydroxyl group leaves as water, generating a carbocation. Now, this is the key step because two possible carbocations can form depending on which hydroxyl group leaves. Pathway A, the top path. If the hydroxyl group on the diphenyl substituted carbon leaves, a carbocation stabilized by two phenyl groups is generated. Phenyl groups stabilize the positive charge through resonance delocalization, making this carbocation highly stable. Then a 1-2 shift occurs, where the adjacent bond migrates and the oxygen donates electrons to form a carbonyl group. This produces product I, which is the cyclohexanone derivative. Pathway B, the bottom path. Alternatively, if the hydroxyl group on the ring carbon leaves first, the resulting carbocation is much less stable because it lacks resonance stabilization from phenyl groups. Although rearrangement could occur, this pathway is energetically unfavorable. Final conclusion. Therefore, the reaction strongly favors the pathway that generates the diphenyl stabilized carbocation. As a result, product I is formed quantitatively, while product 2 is not observed. So the key concept to remember here is carbocation stability controls the direction of the Pinacol rearrangement. In this experiment, chemists wanted to understand whether the reaction proceeds through a free carbocation intermediate. We start with a vicinal diol, where two hydroxyl groups are attached to adjacent carbon atoms. Under acidic conditions, the first step is protonation of one of the hydroxyl groups, converting it into OH2+, which is a very good leaving group. Next, this protonated hydroxyl group leaves as water, generating a carbocation intermediate on the carbon atom. To confirm whether this carbocation actually forms, chemists performed an isotope labeling experiment. Instead of using normal water, they added water containing the heavy oxygen isotope, oxygen 18. Now, if a free carbocation is present in the reaction, the labeled water molecule can attack this positively charged carbon. When this happens, the oxygen 18 from the labeled water becomes incorporated into the product as the hydroxyl group. Experimental analysis indeed shows that the product contains the oxygen 18 isotope in the hydroxyl group. This observation is very important. The labeled oxygen could only appear in the product if external water attacked a free carbocation intermediate. If the reaction had occurred through a concerted mechanism, the oxygen atom in the product would come only from the original diol, and no isotope incorporation would be observed. Therefore, the incorporation of oxygen 18 labeled water into the product clearly proves that the reaction proceeds through a free carbocation intermediate. In this diagram, we see a crossover experiment in the Pinacolone rearrangement used to determine whether the reaction is intramolecular or intermolecular. First, two different pinacols are mixed in the same reaction vessel. One contains an ethyl group and the other contains a methyl group. Under acidic conditions, the reaction begins with protonation of the hydroxyl group, followed by loss of water. This leads to the formation of a carbocation intermediate. Now, the key question is, what happens after this carbocation forms? If the carbocation were completely free and long-lived, it could move around in solution and interact with other molecules. In that case, we would expect mixing of methyl and ethyl groups, leading to crossover products. This possibility is shown in the lower pathway of the image, labeled as the stepwise pathway. Here, intermolecular interaction could generate mixed products. However, these products are marked with crosses, indicating that they are not formed. Instead, the reaction follows the upper pathway, the concerted or intramolecular pathway. In this case, once the carbocation is generated, the 1,2 alkyl shift occurs immediately. The migrating group, either methyl or ethyl, shifts directly to the adjacent carbocation center within the same molecule. Because this migration is fast and internal, the carbocation does not have the opportunity to diffuse or exchange fragments with other molecules. As a result, only the original non-crossover ketones are formed, one from the methyl-containing Pinacol and one from the ethyl-containing Pinacol. So, the absence of crossover products clearly tells us that the rearrangement is intramolecular. To conclude, even though a carbocation intermediate is formed, it remains tightly controlled and the rearrangement proceeds through a direct 1,2 alkyl shift within the same molecule with no intermolecular mixing.